In our last class meeting, we were learning how to utilize our complex power relationships, and we're going to do a little more of that today. So I don't know about you all, but I found that the amount of analysis that we had to do on that in-class assignment problem that we were working, in-class assignment problem number 2, was a little bit tedious. So what I want to introduce to you guys today is some alternative relationships for calculating complex power that we can kind of use as shortcuts. So I want to preface this by saying there is nothing wrong if you happen to choose to always calculate your complex power by doing V times the conjugate of I. That will work 100% of the time. That is the fundamental relationship. What I'm trying to introduce to you guys today is a way to get similar results when you have less information available, so that you can maybe get the results a little bit faster. Okay. So I'm going to call this for right now alternative complex power relationships. And what we're going to be dealing with right now is all predicated on us knowing two things. First, that the definition for our complex power S is simply the product of our RMS voltage multiplied by the complex conjugate of our RMS phasor current. And the other thing that we need to know is just Ohm's law in the RMS frequency domain, which we applied multiple times in Tuesday's class meeting. So Ohm's law in the RMS frequency domain is just going to look like V is equal to I times Z. And what we're going to wind up doing is simply rearranging these two relationships, okay? So let's start with trying to put everything in terms of voltage. So if we only know V and Z, okay? So we could say that our complex power S is going to start as V times I conjugate, our fundamental definition. And so if we don't know what our RMS phasor current is, but we do know what our RMS phasor voltage and our impedance is, we can rearrange Ohm's law, right? So instead of having V is equal to I times Z, we would have I is equal to V over Z, and we can substitute that in. So that would look like V times V over Z conjugate. Well, when I conjugate a fraction, that is the same thing as me taking the conjugate of the numerator and the conjugate of the denominator. So I'm going to write this out a little bit further as V conjugate times V divided by Z conjugate. Now, I don't know whether or not you guys covered this relationship in your ENGT 221 class. So as a quick aside over here, I want to explain to you all what happens when we multiply a particular complex number by its complex conjugate. Okay. So let's say that we have some complex number A, and I'm going to do this in polar form specifically because it'll make the math a little bit easier to follow, but it's not particularly difficult either way. So our complex number A might be represented as A, the magnitude of A, angle theta A, right? That's just our normal polar form complex number. If I had a conjugate, or if I wanted a conjugate, what would that be? So exact same thing, except we would flip the sign on the angle. Exactly right. So we would have the magnitude of A with an angle of negative theta A. So if I were to multiply these two things together, what would I wind up getting? Well, I would have the magnitude of A squared with an angle of theta A minus negative, hold on, that's not right, plus negative theta A. Well, what's theta A minus theta A? Not a trick question. It's just 0, right? So when I multiply any complex number by its complex conjugate, what I'm going to get is just the square of the magnitude of that complex number. So we don't even need to know the whole voltage, right? We don't need to know the phase angle at all if we know the value of the impedance to calculate our complex power. We just need to know the magnitude of the voltage, we square it, and then we divide that by the conjugate of the impedance. And that is our way of calculating complex power for any given impedance if we only know the voltage and the impedance itself. No need for us to try to figure out the current or anything like that. So pretty similarly, we can develop a relationship for if we only know the current and the impedance. So starting with our basic definition, we'll have S is equal to V times I conjugate. And now what we're going to do is we're just going to replace that V with I times Z. Okay. So that's going to look like I times Z multiplied by I conjugate, which is the same thing as I conjugate times I times Z. Well, what's I conjugate times I? Disagree. So it's the magnitude of the current squared, right? So we did that right up here. The only thing that remains is the magnitude of the current, or the magnitude of the complex number squared. So we're just going to have simply the magnitude of our current squared times the impedance itself. No conjugate on this guy. Okay. So I'm going to put a box around these relationships. So S could be expressed as the magnitude of the voltage squared over Z conjugate, or we could have it as the magnitude of the current squared times Z. So what I want us to do now is actually use these relationships so that we can infer a couple of things about how resistors, capacitors, and inductors are going to behave in these AC circuits, okay? So what is the impedance of a resistor? Does anybody remember that from your 221 class? That is a little scary. So for a resistor, I'll do this as an aside over here on the right. So impedance in general is going to be the ratio of phasor voltage to phasor current, okay? So for a resistor, that's literally just going to be the resistor value itself. So when we go from the time domain into the phasor domain, resistors stay resistors, nothing fancy there, okay? Inductors have an impedance of J omega L. Does that sound familiar? Okay. And we could also write this as simply J X sub L, where X sub L is just the reactance of our inductor, which is simply omega L. And for a capacitor, our impedance is 1 over j omega c, or negative j xc, where xc is the reactance of the capacitor, which in this case would be 1 over omega c. Okay? So for a resistor, our complex power relationship, so let's call this S sub R. So we're talking specifically just for a pure resistance. We would have the magnitude of the voltage squared divided by the conjugate of the impedance of a resistor. So if a resistor in rectangular form has an impedance of R plus J0, what would the conjugate of that impedance be? Yeah, so it would be R minus J0, which is still just R. So effectively, because a resistor is purely real, the conjugate is the same thing as the not conjugate, okay? So we would just have the magnitude of the voltage squared divided by R, which for what it's worth, that looks exactly like the old school relationship for the power absorbed by a resistor from your DC circuits, right? Just V squared over R. But now we're just using the magnitude of the RMS voltage instead of a DC voltage. And hopefully that makes sense because our RMS voltages, if you recall from when we were talking about on our first day of class, is a DC equivalent representation of those AC signals. So it should make perfect sense that we essentially wind up with the same DC relationship. My relationship in terms of current is just going to be the magnitude of the current squared times my impedance, where my impedance in this case is simply R. So what can we say about this complex power? So the magnitude of the voltage is a real number, right? It's not a complex number. There is no imaginary part. We square that, the resistance is a real number. So we have a real number over a real number. So it seems like our complex power absorbed by a resistor is always purely real. So we are going to say that resistors' job in these circuits is to absorb real power, or what we would normally call average power. And I'm saying that they absorb average power because we're always going to get a positive number. So anytime we have a negative number, we would be supplying power, okay? So before we move on to inductors and capacitors, does anybody have a question about how we got here? It's literally just applying those two equations that I boxed in red above, and then I'm just substituting in the value of the impedance. So for an inductor, we are going to have S sub L is going to be the magnitude of the voltage squared divided by the conjugate of the impedance of our inductor. So what is the conjugate of our inductor impedance? So I have it written up there as ZL is equal to J omega L. So what's the conjugate of J omega L? Negative J omega L. Absolutely right. Now, as a quick aside here, I want to show to you guys that 1 over negative J is the same thing as just positive J in the numerator, okay? So if I have 1 over J, and I multiply that by J over J, I would have J divided by J squared, which is, so what is J? Let's start there, actually. You guys remember that? Right, so what is fundamentally? Square root of -1. So if I have the square root of -1 squared, what do I get? -1. So 1 over J is -J. So 1 over -J should come out to give us positive J. So I could write this as J omega L times the magnitude of my voltage squared, or I could put it as J XL times the magnitude of my voltage squared. If I wasn't given my frequency and inductance value, if I was just given the reactance, which will happen at times, this is how I can calculate that complex power, only knowing impedance or reactance and voltage. Down here below, let's look at what's happening with our current relationship, right? So we should just have the magnitude of our current squared, sorry, times J omega L. Oh, my goodness, I made a huge mistake here. Sorry about that. So this should have been the magnitude of the voltage squared over omega L, or the magnitude of the voltage squared over XL. My apologies for that. Instead of moving just the minus J to positive J in the numerator, I accidentally moved the whole damn thing. So my apologies. Hopefully I have unconfused you. If you weren't figuring out how the hell I did that, it was a mistake. All right, so we have I squared times J omega L. So I could write that as J times omega L times the magnitude of the current squared, or JXL times the magnitude of the current squared. So what can we see from these relationships? Okay. So first thing I can notice is that I'm always going to get a positive result again, because XL should always be positive. And whenever I square my voltage or square my current, that's always going to be a positive number as well. So it's always positive, but it's also always imaginary because there's a factor of J out in front. So my complex power has no real part. It only has a positive imaginary part. So that means that inductors work to absorb reactive power. Okay. So any inductor I have is always going to be absorbing reactive or imaginary power. Okay. Lastly, we have capacitors. So we are going to have S sub C is going to be equal to the magnitude of our voltage squared divided by the conjugate of our impedance. So our impedance is 1 over J omega C, and I need to change the sign on the J to do the conjugate operation. So I have essentially a factor of 1 over 1 over negative J. So that's going to look like a negative J up in my numerator, okay? And I have a 1 over 1 over omega C, which is going to look like a factor of omega C in my numerator as well. So I'll have negative J omega C times the magnitude of my voltage squared. put in terms of current, I'm going to have the magnitude of my current squared times 1 over j omega c. Actually, sorry, let me go back up here really quick like. So this is going to look like negative j times the magnitude of my voltage squared over xc in terms of reactance. Coming back down here, sorry for that pickup. I'm going to have, let's see, 1 over j is negative j. So I'm going to have negative j times the magnitude of my current squared divided by omega c. And that's going to be the same as negative j times xc times the magnitude of my current squared. So what can we observe about these relationships? They're both always going to be negative because there's a negative sign out front, and the voltage squared is always going to be a positive quantity, and xc is going to be a positive quantity. So we have something that's always negative, and it's also always imaginary because there's a factor of j out in front. So if inductors absorbed reactive power because they had a plus j relationship, then we could say that capacitors have to be doing the opposite of absorbing power because the negative sign, which means we're going to say that they supply reactive power. All right, so I want to revisit our in-class assignment from our last class meeting here really quickly. I want us to look back at problem 2. We're not going to rework the whole thing again because that would be a waste of our time. I just want to show you very simply that we could have used these alternative relationships where once we found these 3 currents, we could have used them to do to calculate our complex power and all of that kind of good stuff. So let's just look at that current IA, right? So here in part A, we were asked to determine the average power absorbed by our impedance ZA. And we took the entire equivalent impedance of our network, divided our source voltage by that ZEQ in order to come up with IA. So what I want us to see really quickly is if we take the relationship that SA is going to be the magnitude of IA squared times ZA, do we get the exact same result as doing it the quote unquote long way that we did in class on Tuesday? Okay. So what would the magnitude of IA be? (14.657 amps. Absolutely right. So it's not the phase angle part of IA, it's the other part. So 14.657 amps squared, and then our impedance ZA was 2 angle 15. That ohm symbol looks particularly shitty. So I'd like for you guys to throw this into your calculator. And tell me what you get. Let's do polar form. All right. So 429.655 angle of 15 degrees volt amperes, that is exactly what I got. So all I'm going to do now is I'm going to scroll down and I'll be damned if I didn't get the exact same result, right? So we've derived everything correctly. So the benefit of this method up here that we did is that we literally only need to know the magnitude of the current and the impedance itself. We didn't need to take those extra steps in finding the voltage, multiplying, the voltage times the complex conjugate of the current, all that kind of stuff. That's just a faster way to do it. So I wanted to make sure that you guys were aware of those relationships in case you want to utilize them, okay? So let's move on to problem 3. So in this circuit, we have a composite load formed of these loads Z1, Z2, and Z3. Now, we aren't told what the impedance of these loads are. Instead, we are told information about the complex power that they are absorbing. So for instance, we're told that one load, let's call it the load Z1, is drawing 100 watts at a power factor of 0.92. Our second load is drawing 250 watts at a power factor of 0.8 leading. And our load Z3 is drawing 150 watts at a power factor of 1. So what I want us to do here is to determine from just those brief pieces of information the complex power absorbed by each of those 3 loads, right? So in our problem statement, we are told that P1 is 100 watts and the power factor for load 1 is 0.92 lagging. So how could we use those 2 pieces of information to determine the complex power absorbed by that particular load? For what it's worth, we did something very similar to this, or a calculation very similar to this, in the first problem to this in-class assignment. So if you need to flip back to that work to look at how we did it then, please do so. I believe it would have been part C or part D of problem 1. So P divided by PF. So I'm just going to put the subscripts 1 here. So that's going to give me my apparent power. Okay. Okay. So in problem, I think it was problem 1, part D, if I'm remembering correctly, we had a load that was operating at a leading power factor. And so that's why we had the negative sign in front of that arc cosine operation, right? Because we know whenever our power factor angle is a negative, we have a leading power factor. Whenever our power factor angle is positive, we have a lagging power factor. We are told here specifically that load 1 is operating at a lagging power factor. So I need to make sure that that inverse cosine operation or that arc cosine operation returns a positive angle. So that's why this guy is getting a plus sign and part D from problem 1 got a minus sign. It was operating at leading, okay? So we can throw this into our calculators. So I'm going to do that. That's just 100 divided by 0.92 with an angle of inverse cosine of 0.92. And I got 108.696 with an angle of 23.073 Let me make sure that's rounding correctly. Nope, 074 degrees, volt amperes. And I'm going to store this in my calculator as X. So before we move on from this, did anybody else get a similar result? Okay. And if your result isn't similar, make sure that you're getting the answer in polar form as I have it written here, because obviously rectangular form is going to give you different numbers. So for our second load, we are told that it's drawing 250 watts at a power factor of 0.8 leading. So using this information, how would I calculate the complex power absorbed by load 2? Yes, sir.
How do I store the variable?
It was 36, that, right?
Yeah, you're the one that's, we also.
Or X.
Okay.
Well, that happened.
Do the same thing.
So pretty much the exact same thing. What's going to be the difference here? So we're going to have to put a negative sign in front of the arc cosine operation. Exactly right. Everything else will be exactly the same. So we would have P2 over PF2 with an angle of inverse cosine of PF2. So I'm going to plug those numbers into my calculator. So 250 over 0.8 with an angle of negative inverse cosine of 0.8. I got 312.5 with an angle of negative 36.870 degrees volt amperes. And I just stored that in my calculator as Y. So before we move on from this step, did everybody else get that same result? Good deal. For our last load, we are told that it's drawing 150 watts. So P3 is equal to 150 watts. And we're told that our power factor is unity, or 1.00. So technically, we could do the exact same thing to find our complex power as we've done for the previous two steps, but realistically, that's overkill, right? So what does it mean when our power factor is 1? The average power and the apparent power are literally the exact same thing, okay? So instead of going through the math here, anytime I have a unity power factor, I can literally just say that I'm going to have whatever power I'm told with an angle of 0 degrees. Recall from when we were discussing power factor that a power factor angle of 0 corresponded to a power factor of 1, right? So we could type that whole big thing into our calculator if we were so inclined, but we wind up getting just the same result by understanding what unity power factor actually means. Okay. So I'm going to put this in my calculator and store it as Z. Okay. So we've got some of our groundwork taken care of. Let's take a look at what we're asked to do here. Okay. So in part A, we are asked to determine the power factor of the composite load. So the composite load simply means what happens if I lump all three of those loads together, okay? So how would I determine the total complex power absorbed by my composite load? Anybody have any thoughts? This isn't meant to be a trick question or anything like that. Add them all together, 100% correct. It is as simple as that. So we're gonna have S1 plus S2 plus S3. And because I stored all of those values in my calculator, I'm literally just gonna do X plus Y plus Z. And I wound up getting, 520.573 with an angle of negative 16.162 degrees volt amperes. So, did anybody else get this result? Let's start there. Got some thumbs up. Great job. All right. So how can I use this information to determine the power factor at which my composite load is working, which I'm going to call PF comp? Cosine of that angle, absolutely right. So that'll be the cosine of negative 16.162 degrees. So cosine of the angle of what I have stored in my calculator, as T. I got 0.9604, so let's call this 0.960. Is this power factor leading or lagging? So I hear one person saying lagging and one person saying leading. Person who's saying leading is correct. Tell me why you're correct. Exactly right. Anytime we have a negative power factor angle, we will be operating at a leading power factor. Good job. All right. So in part B, we are asked to determine the RMS current flowing through our source. Okay. So we are told that the voltage drop across our composite load is 115 angle 0 degrees volts RMS. Okay. And we're trying to find our source current. Okay. So if we look at this picture that's representing our system, our current IS, all of it flows through that 10 ohm resistor, and then all of it is going to flow to this node point before it's going to divide up among those three loads that form our composite load. So in order for us to calculate our current IS, there are there are two different ways that I can think of to do this, okay? So one is we could use the complex power for each individual load, solve for the current flowing through each load, and then add those currents together using Kirchhoff's current law to give us IS. Or, because we know the voltage drop across our composite load, we can just use the total complex power absorbed by our composite load to get IS without having to do all that KCL stuff. So that's probably the way that I would tend to do it because it's a little bit faster, okay? It did require us to figure out the total complex power absorbed by the composite load, but we had to do that anyway for the first part of our problem, okay? So for part B here, we know that S composite is going to be equal to the value of our load voltage multiplied by the complex conjugate of our source current. Okay, that's just S is equal to V times I conjugate, where the voltage drop across our composite load is VL, and the total current entering our composite load is IS. Okay. So stands to reason that we could algebraically rearrange this guy, I hope pretty easily, to solve for IS. So if we divide both sides by VL, we're going to wind up having IS conjugate is equal to S composite divided by VL. So how do you guys think I can get rid of that conjugate there? I mean, realistically, I could just do this math and then flip the sign, but there's a slightly smarter way to do it. Yes.
How do you V out to the VS?
So, good question. Okay. So first is we don't know what VS is. That's actually part C that we're going to do next. So we only know the complex power that is absorbed by those three loads there. And we know that VL is the voltage drop across those three loads because they're all connected in parallel. So that's the only voltage we have. That's the only complex power we know. So that's the only way we can currently solve for IS, essentially. Yeah. If we had VS, what we would wind up doing probably is trying to figure out the complex power absorbed by that 10 ohm resistor, adding that to our composite load, and then doing the same process using VS instead of VL. So, coming back to my question from a moment ago, how am I going to get rid of that conjugate? So what does the conjugate operation do? Remind me of that, please. Think about it in terms of a polar form complex number. Switches the sign on the angle, okay? So if I did a second conjugate operation, I would switch the sign back. So if I just take the conjugate of both sides, I will actually wind up getting rid of that conjugate, and I'll be left with a conjugate over here. And recall from a few minutes ago when I talked about taking the conjugate of a fraction, that's the same thing as taking the conjugate of the numerator over the conjugate of the denominator. So I'm just going to choose to write this as S composite conjugate over VL conjugate. Okay. So what is S composite conjugate going to be? What was that? So 520.573 angle positive 16.162 degrees volt ampere, because the conjugate operation simply switches the sign of the angle on the polar form complex number. Okay. If VL is 115 angle 0, what's VL conjugate? 115 angle -0. So anytime we have something that's purely real, the conjugate operation doesn't actually do anything. So I'm going to put this down as 115 angle -0 degrees, volts RMS, just to remind us that we're supposed to flip the sign on that angle when we perform the conjugate operation. So when I throw this into my calculator, so let's see, I'm going to have the conjugate of what I have stored as T divided by 115, I get 4.5267, so 4.527 with an angle of 16.162 degrees. amps RMS. Exactly what I got there. So before we move on to part C, does anybody have any more questions about what we've done here? All right. So in part C, we are asked to find the voltage that is supplied by our source. I specifically want the full RMS phasor voltage. Okay. So does anybody have any thoughts on how we might solve for VS now that we know VL and IS? Brandon. So if I multiply VL times IS, that's going to give me the conjugate of the complex power that was absorbed by our composite load, and we already know that, so that's not really bringing anything new to the table. So we can't use voltage division here because we don't know what those impedances Z1, Z2, and Z3 are. That's a good suggestion, but because we were given information about the power absorbed by those loads instead of the impedance of those loads, voltage division isn't going to work out for us. So it's a fundamental relationship, right? How many of you guys remember what Kirchhoff's voltage law is? All right. So Kirchhoff's voltage law tells us that the sum of the voltage drops around any closed path must be equal to 0. So essentially what I am suggesting we do is perform KVL around this path because it's starting at this bottom node and it's ending at that bottom node. So we could say that our source voltage VS is just the voltage drop across that 10 ohm resistor plus VL, which we already know. So if I call this voltage right here, or I don't know why my stylus is being a little odd. So if I call that voltage V10, I would have goodness gracious, this is annoying me. Oh, good God, I don't want to open up OneNote. I hate OneNote so much. V10 plus VL. Let me save this and then close out of this program just so I can see if my stylus will stop drawing so damn sloppily here. My penmanship is bad enough. I don't need you guys struggling with just extra stray pen marks and all of that kind of stuff. Okay, good. It did save that. All right. Let's cross our fingers that this looks wildly less shitty. VS, that's still being dumb, is equal to V10 plus VL. I will probably go back through in my office hours and rewrite this to look less shitty, but we need to move along here. So how would I solve for the voltage drop across my 10 ohm resistor? Let me scroll up to the circuit. Yeah, absolutely right. Just Ohm's law. V is equal to I times R. Yeah. So that'll just be 10 ohms times IS. Where IS was that 4.527 with an angle of 16.162 degrees amps RMS. Oh my God, this looks so horrifying. Plus 115 angle 0 degrees volts RMS. So when I put that into my calculator, I got 158.978 with an angle of 4.546 degrees volts RMS. See if I can do this with this cheap knockoff stylus and have it look less shitty. So did anybody else get that result? Let's start there. If you can read that terrible chicken scratch looking shit. It says 158.978 with an angle of 4.546 degrees. Yay or nay? Good deal. All right. So that's our source voltage. The last thing that we are asked to determine is the power factor at which our voltage source is supplying power. Okay. So we now know our source voltage, Vs, we just solved for it. We know our source current from step step B. And so now we're just going to calculate the complex power for the whole system. And then use that information to find our power factor, right? So we could say that the complex power absorbed by our voltage source, which is going to be SVS, should just be VS times IS conjugate. So that would be 158.978 with an angle of 4.546 degrees volts RMS. The conjugate of our current will be 4.527 with an angle of negative 16.162 degrees amps RMS. And when I put that into my calculator, so let's see, let me store that as B. So B multiplied by the conjugate of what I had stored as A. I got 719.651 with an angle of negative 11.616 degrees. So the power factor at which my voltage source is supplying power, how would I determine that? Cosine of that angle, sure. So let's see, cosine of argument of my prior answer. I got 0.9795, so I'm going to call that 0.980. And is that leading or lagging? Why is it leading? Why did you change your answer? Because it's a negative angle. Absolutely right. So 0.980 leading. Let me see if my good stylus. All right, it stopped having the trailing bullshit because this thing sucks around. Great. Okay, so we're finished with in-class assignment number 3. For those of you who are not here to watch not here to work on problems 1 and 2 with us on Tuesday, this is the one and only time I will allow you to go back through and rewatch that lecture video because we worked those first 2 problems in, and you can turn in ICA number 1 late to make up for the fact that you weren't in class on Tuesday. From here on out, all of our in-class assignments are going to be due at the end of the class that we're doing them because that's what they're for, is a participation grade, okay? Okay, so what I want to talk about now is the concept of power factor correction, okay? So when we talked about power factor in our last class meeting, I introduced it to you all as the ratio of the average power, which is what we as consumers pay for, to the apparent power, which is what the electrical utility pays to produce, okay? I also mentioned to you that quite obviously the electrical utility wants that ratio to be as close to 1 as possible so that they're not producing extra electricity that just winds up getting sent right back to them, okay? So in an industrial setting, if your manufacturing plant or whatever operates at too low of a power factor, the electrical utility will fine you, okay? So in order to avoid those fines, industrial consumers perform a process that is called power factor correction, which is trying to raise their power factor above some threshold target power factor. And that threshold depends on the utility itself. So some utilities might use 95%, other utilities might use 97.5 or 98%. Generally speaking, the utility doesn't care whether or not you're operating at a leading or lagging power factor. They just want you to be very, very close to 1, okay? So what we're going to do is essentially try to figure out how this concept of power factor correction works, okay? So I'm going to look at the power triangle for an inductive load because the overwhelming majority of the time, we are going to be dealing with inductive loads because of things like induction machines, synchronous machines, all that kind of stuff. They all have big coils of wire in them, which behave like inductors. And so 99.99% of the time, the loads that we are going to try to power factor correct or power factor compensate will be inductive loads, okay? So the power triangle for an inductive load, and we addressed this at the beginning of class on Tuesday, would look something like this, right? We'd have some, here's our complex plane, and our complex power vector S would be here in the first quadrant. And I'm going to call this S old, and it's representing the complex power before we apply our power factor correction technique, okay? So that means that the projection of S old onto the real axis would be P old. the projection of S old onto the imaginary axis would be Q old. And the angle formed between the positive real axis and our S old complex power vector would be theta old. Okay. So if we want to operate at a higher power factor, or a power factor that is closer to 1, do we need to make theta old larger or smaller? Smaller, right? Because cosine of 0 is 1. So we were trying to make theta old as close to 0 as possible. So we need to make this angle smaller, okay? So let's talk about how we can make this angle smaller, okay? So we are going to assume that we're going to try to hold P old to be constant, okay? So let me explain that really quickly. Technically speaking, if I increase the amount of average power that I am consuming while keeping everything else the same, my angle will get smaller. However, average power is what we pay for. So that would be like me running up my utility bill in order to avoid paying a fine. Doesn't make a lot of practical sense, okay? So if we keep P old to be constant, if we lower Q old, then that's going to make that angle smaller, right? So we might have something like this. So let's say that this light purple vector could represent S nu, okay? Where this would represent Q nu, and this angle would represent theta nu, right? So if we are able to somehow lower the amount of reactive power that is being absorbed by our system, we should see that our power factor is increased. So now this begs the question of how am I going to lower the amount of absorbed reactive power in my system? It would be convenient if there was something that we could add that effectively supplies reactive power in order to counteract some of the reactive power that's being absorbed. Well, what did we learn about maybe 15 minutes ago that that supplies reactive power? Capacitors, absolutely right. So what we're going to do in order to correct the power factor in an industrial setting is we are going to put a big capacitor. Typically speaking, it will be in parallel with our voltage source, so that it'll compensate for any stray inductance in our transmission lines as well as the connected equipment, okay? So we're going to use a capacitor in parallel with our system in order to improve the power factor at which our system as a whole operates. So let's look at the math behind this, okay? So I'm going to say that S old in rectangular form is P old plus J Q old, right? And that's exactly what I've indicated on my power triangle. And I'm going to say that S nu is equal to P old plus J Q nu. So the complex power that needs to be provided by my capacitor is essentially just going to be the difference of those two things, where S nu is the power after we've met our specific power factor correction goal, right? So let's say that SC So complex power absorbed by our capacitor is going to be simply S new minus S old. So that's going to look like P old plus JQ old minus P old plus JQ new. So I have P old minus P old. So my capacitor will not need to be providing any real power, which we know that it can't anyway. And so I'm going to be left with J. Sorry, I got these backwards. That one should be new. And that one should be old. Sorry about that. I'm going to be left with J Q new minus Q old, where Q new minus Q old is always going to be a negative quantity that I'm going to call Q cap. Okay. So we have this relationship for the complex power absorbed by our capacitors. When we were investigating those alternative relationships, and we have them literally right here, I can see that the complex power absorbed by a capacitor can also be written as negative J omega C times the magnitude of my voltage squared. And so if I put those guys together and rearrange, I can solve for the value of the capacitor that will allow me to hit some target power factor correction goal. Okay. So that relationship is going to be C is equal to negative Q cap. So since Q cap is always negative, putting an extra negative sign there is going to turn that into a positive quantity because we're going to want our capacitor to be some positive value. They don't make negative capacitors. Divided by omega times the magnitude of the voltage across the capacitor squared. Now, this relationship is 100% correct, but it's not particularly easy to use because it's not intuitive as to how we would input information about, let's say, what our target power factor is or what our current power factor is or anything like that. So we can actually expand on this relationship a little bit. It's going to look slightly more complicated mathematically, but it's actually easier to use if we express this relationship as P old times the tangent of theta old minus the tangent of theta new. For what it's worth, that numerator is literally just Q cap divided by, negative Q cap divided by omega times the voltage drop across our capacitor squared. So essentially, we can't put in our power factors directly, but we can put in our power factor angles, which we can get from our power factors really easily. And so we can literally just put in system information in order to calculate the value of the necessary capacitor, okay? So I'm going to open up in-class assignment number 2, and we are going to look at how to apply this relationship. So just to remind us, I'm going to just start by writing down my relationship to find C. Yes. Sure. Yes,
So is omega the two pi hertz thing?
exactly right. Yeah, so omega is our angular frequency, and it is exactly equal to 2 pi times our linear frequency, where linear frequency is indeed measured in hertz. Yes, great job. Mark, Tucker, you guys good? All right. So our equation, just to remind us, is P old times the tangent of theta old minus the tangent of theta new, all divided by omega times the voltage drop across our capacitor squared. So in our problem description here, we are told that we have a 230 volt RMS source operating at 50 hertz, and it is powering a single phase induction motor with an impedance of Z motor is equal to 25 plus J10. And our ultimate goal here is to figure out what value of capacitor is needed to raise the power factor of the motor to unity. Right? So if I were to try to draw a schematic diagram for this system, it would be something like this. Okay. So here's my source voltage. So we have 230 volts RMS at a frequency of 50 hertz. So there's my supply. And then over on this side, I have my motor, whose impedance Z motor is equal to 25 plus J10 ohms. So we need to figure out how to take in that information and determine P old, theta new, omega, and the magnitude of the voltage drop across our capacitor. And for what it's worth, our capacitor, I'm going to put it in green here, is going to be applied across the terminals of our motor or supply voltage, in this case, that are the same terminals, right? So that's where our capacitor is going to go in this system that's used to correct our power factor. So let's start with any low-hanging fruit we might have, okay? So looking at this schematic diagram, what is the value of the voltage drop across our capacitor? $230 volts, right? So that 230 volt source is in parallel with that capacitor. So it looks to me like the magnitude of the voltage drop across our capacitor is 230 volts RMS. Anybody have any questions, comments, or concerns about that observation? All right. Ricky, tell me how we would get our angular frequency omega.
You do 2 pi times.
2 pi times our linear frequency of 50 hertz. Exactly right. So omega is always just going to be 2 pi f. So that's going to look like 100 pi radians per second from our linear frequency of 50 hertz. So 2 pi times 50 is just 100 pi. Okay. So those are the easiest things for us to figure out here. Now we're going to have to do a little bit of work, okay? So the next easiest thing to figure out would probably be theta nu, okay? So we are told that our target power factor should be 1 or unity. So if I know that my target power factor is unity, what does theta nu, the angle after power factor correction, have to be? 0, okay? So theta nu is going to be the inverse cosine of 1, which is 0 degrees. Absolutely right. So the only two things left for us to figure out is the average power that is being absorbed by our motor, which is P old, and the power factor angle that our motor is operating at before we apply power factor correction, okay? So essentially, we could get both of those pieces of information if we were able to determine the complex power absorbed by our motor prior to power factor correction. So what do we know? We know the voltage drop across our motor, or at least the magnitude of the voltage drop across our motor, and we know the impedance of our motor. So do we have a relationship for calculating complex power if we only know the magnitude of the voltage and the impedance? No. Ohm's law with those two pieces of information would give us current. Right? V is equal to IZ, so we could do I is equal to V over Z, but that is not complex power. We could use that current to calculate complex power, but there's an easier way. We talked about it earlier in this class meeting. Magnitude of the voltage squared over, is it just over the impedance or over the conjugate of the impedance? Conjugate of the impedance, okay? So we could say that S motor is equal to the magnitude of the voltage squared divided by the impedance of the motor conjugate. So that would be 230 volts RMS quantity squared. How do I do the conjugate of 25 plus J10? 25 minus J10. Absolutely correct. Great job. And I will wind up getting 1,964.657 with an angle of 21.801 degrees, volt amperes in polar form, which is the same as 1824.138 plus J 729 0.655 volt amperes in rectangular form. So using these results for my complex power calculation, which of these four numbers is P old? Brandon. Exactly right. Average power, P old, is going to be the real part of our complex power, 1,824.138 watts. Great job. So I'm just going to make a note over here. P old is equal to 1824.138 watts. Okay? How am I going to find theta old? Exactly right. It's just 21.801 degrees, 100%. .801 degrees is theta old. And so now I have all of the necessary information to just plug into my equation to calculate the value of that capacitor. So it's just plug and chug at this point, right? So we're going to say that C needs to be 1824.138 watts multiplied by the tangent of 21.801 degrees minus the tangent of 0 degrees, all divided by 100 pi radians per second multiplied by 230 volts RMS quantity squared. And I'm going to put that into my calculator real quick. So I got, let me put it down here, 0.000043905 farads, which could be better expressed as, let's see, 1, 2, 3, 4, 5, 6, 43.905 microfarads. That looks too much like an A. And I'll be damned if that isn't the correct answer. Okay. So for these power factor correction problems, and we're going to work one that's a little bit more complicated here in a moment. It's literally just how do I get the pieces of information to plug into that equation, and then I plug and chug. What's up?
For the 100 pi radians per second, why doesn't that like mess with the angle like?
So a radian is a dimensionless quantity, okay? So realistically, we could just call that 100 pi per second, and the units will work out to exactly give us farads, because a farad is an amp second per volt, if I'm remembering correctly, right? So just looking at things here dimensionally, we are going to have watts, which is amps times volts, divided by something that is in per seconds times volts, right? So this volt is, shit, I didn't change the color. This volt is going to cancel this volt. 1 over a second is the same thing as putting a second in the numerator. And so we have amp seconds per volts, which is a farad. Yeah. We are not going to, or let me rephrase it. It is not my intention to ever kind of mess with you guys regarding the units of our angles and stuff like that. So I'm not going to try to throw you guys any curveball and seeing if you're picking up on that stuff. I'm just trying to make this as straightforward and practically applicable as possible. Okay. I saved that dickery for my other classes. Okay, so how did you guys feel about this example? Nothing too wild or crazy, I don't think. So let's look at in-class assignment problem 2 and see if we can get this guy knocked out prior to the end of class here. So we're told that we have a transformer that's supplying power. So the secondary windings of our transformer are really just going to be playing the role of a voltage source in this system, okay? And it's supplying power to an industrial load through a transmission line that has an impedance of 0.1 plus J 0.2 ohms. Our system is operating at 60 hertz, and the voltage at the load is 480 with an angle of 0 degrees. We're told that our load is consuming 125 kilowatts at 0.88 lagging, and we're asked to determine complex power absorbed by the load, complex power absorbed by the transmission line, complex power being supplied by our transformer, and then finally the capacitor value needed to improve our power factor up to 0.975 lagging. So this problem right here is kind of tying in together everything that we've done up to this point in the class. So I'm going to draw a picture. So as I mentioned earlier, our transformer is playing the role of a voltage source here, and we do not know what this voltage is. It was not provided to us, so I'm just going to leave that as Vs. Okay. Excuse me. This impedance right here is going to represent our wire, our transmission line. We are told that it has an impedance of 0.1 plus J 0.2 ohms. And then over on this side, we have our industrial load. And we are told that our industrial load is drawing 125 kilowatts at a power factor of 0.88 lagging. So there is our graphical representation of our system. We are also told that the voltage drop across our load is 480 angle 0 degrees volts RMS. So in part A, we are asked to determine the complex power being absorbed by our load. So how are we going to do that? So what do we know about our load? We know it's absorbing 125 kilowatts of power. And we know that it's operating at a power factor of 0.88 lagging. So I believe pretty strongly that we have calculated complex power from only knowing those two pieces of information, I think at 4 different points today. Might have only been 3, but either way. P average over the power factor with an angle of the inverse cosine of the power factor. Yep. So 125 kilowatts divided by 0.88 with an angle of inverse cosine of 0.88. Now, since my power factor is lagging, should that inverse cosine operation get a plus sign or a minus sign? Plus sign, absolutely right. All right, so let's throw this into our calculators. 125 over 0.88. Angle inverse cosine of 0.88. I got 142.045 with an angle of 28.357 degrees kilovolt amperes. So if I have my power is in kilowatts, excuse me, my average power is in kilowatts, my complex power is going to be in kilovolt amperes. And I'm storing this for later in my calculator as X. For what it's worth, because I know here in part B, we're asked to calculate the complex power being absorbed by my transmission line. I feel like it's going to be smaller, so I saved it in my calculator in volt amperes just in case. Yes, Tucker.
Kilowatts, could you keep it like that, or will we like change it to 125,000 watts?
So I personally just changed it to put it into 125,000 watts, essentially. The reason why I did that is because I know at the end, I'm going to be calculating my capacitance value. And I have a feeling, a pretty strong feeling for what it's worth, that the value of my voltage is going to be measured in, across my source is going to be measured in volts. And so I want to make sure that the thing that I'm getting at the end is going to be just in farads, not in microfarads or kilofarads or something weird like that. So I usually bring things down to the base units just to make sure that everything's going to work out okay. Okay. So we answered part A. Everybody, I hope, is catching what we're throwing there because we've done that so many times today. For part B, we're trying to find the complex power absorbed by our transmission line, okay? So it may not be obvious, but we have actually done this type of calculation before as well. So if we look back at this last problem for this ICA, that 10 ohm resistor is pretty much playing the role of the impedance of the transmission line, okay? So what we are going to do is something similar to this. We're going to solve for the current that's flowing through the transmission line because that's going to be the easiest piece of information that we can get in order for us to solve for that complex power. So in this particular problem, we solved for that current IS by taking the complex power absorbed by our total load and then kind of working backwards to solve for I. I'm going to use that exact same relationship here without the derivation because we've already seen how that works, okay? So I'm going to say that the current that's leaving my source, IS, and I'm going to indicate this on my diagram, is going to be S load, sorry, it should be lowercase, conjugate over VL conjugate, where S load conjugate is going to be 142.045. And I'm going to put times 10 to the 3 to put things in volt amperes with an angle of negative 28.357 degrees VA. The negative sign there is coming from the conjugate operation. And I'm going to divide this by 480 angle negative 0 degrees volts RMS. And let's see. So crap. I want the conjugate of what I have stored in my calculator is X divided by 480. So I got 295.928 with an angle of negative 28.358 degrees. Did anybody else get a similar result when they calculated their current? All right. So how can I use this current to calculate the complex power absorbed by that transmission line impedance? So what I know is the current flowing through the line and the impedance of the line. So I feel pretty strongly that we introduced a relationship that would allow us to calculate complex power only knowing those two pieces of information earlier. So what was that relationship?
Squared.
Exactly right. Thank you. So that's going to be 295.928 amps RMS squared times 0.1 plus J 0.2 ohms. Making sure I got that right. Yep. Okay, so I want the magnitude of what I have stored in my calculator as Y squared multiplied by 0.1 plus 0.2 I. And I got 19.582 with an angle of 63.435 degrees kilovolt amperes. And I'm going to store that as Z. Yes, sir.
Why can we use the voltage?
We don't know the voltage drop across the wire.
Oh.
We only know the current flowing through the wire. So that's what we used. We could, for what it's worth, have used Ohm's law. So once we found IS, we could find the voltage drop just across the wire and then use the magnitude of that voltage over the impedance, but that's just introducing an extra step to find that voltage. Any other questions about what we did here for part B? So in part C, we are asked to find the complex power being supplied by our transformer. So anybody have any thoughts on how we're going to do that? I'm going to scroll back up so we can see our system. Mark.
Sorry, what did you describe as the introduction?
Repeat the question. I wasn't
describing CS, what it's looking for.
C. Well, oh, what are we looking for in part C? Sorry. So we're trying to find the complex power that is being supplied by our transformer. Anybody have any thoughts? Can anybody tell me what the law of conservation of energy is? Energy can't be created or destroyed. Okay, fair enough. So in the context of circuits, we usually put that as, however much power that we have supplied by our source has to be equal to the total amount of power absorbed by our load. So I'm trying to find the complex power supplied by my source, and I know the power absorbed by my transmission lines, and I know the power absorbed by my load. So how would I use that information to calculate the complex power supplied by my source? Add them together. Absolutely right. So SVS is just going to be S wire plus S load. Power in equals power out. So for me, this is just what I have stored in my calculator as X plus what I have stored in my calculator as Z. So X plus Z is going to give me 158.471 with an angle of 32.4297. So let's call this 430 degrees kilovolt amperes. And for reasons that will become obvious in a moment, I'm also going to express this in polar form, or excuse me, rectangular form, which would be 133.757 plus J 84.980 kilovolt amperes in rectangular. So does anybody have any questions, comments, or concerns about what we did for part C here? Okay. So the last thing that we need to do is take this information and figure out the value of the capacitor. So our capacitor in this case would be applied here across the terminals of our transformer in order to correct the power factor of the whole system. So we're trying to find the value of that capacitor, which is going to improve its power factor to 0.975 lagging. So down here for part D, we are going to be applying this equation. C is equal to P old times the tangent of theta old minus the tangent of theta new all over omega times the voltage drop across our capacitor squared. So let's start checking things off that we know. Okay. Do we know P old? So P old would be the average power supplied by our transformer prior to power factor correction. Do we know that?
125 kilowatts.
So 125 kilowatts is the average power that was absorbed by our load, but it's not going to be the same thing as the average power absorbed, or it's going to be supplied by our source, because our transmission lines are absorbing some average power as well. I mean, possibly, but for what it's worth, it's literally already written down up here somewhere. I want you guys to figure out where it is. Where the hell did you get 28.35 from? Oh,
And the angle of S load.
no. So we are trying to correct our power factor on the source side of things. So we need to be looking at what's going on with our source, right? So in part C, we calculated the complex power that was being supplied by our source. And what I'm trying to find is the average power that's being supplied by our source. So that number should be somewhere in our answer for part C, 133.757. That is going to be P old. That's our average power that's being supplied. Okay. What is theta old going to be? So this is the power factor angle of our system prior to power factor correction. 32.43, absolutely right. Okay. So theta new, we don't know it yet, but we can get it pretty easily, right? So theta new represents what our power factor angle will be after power factor correction. And we are told in our problem statement that we're trying to hit 0.975 lagging. So how would I use that power factor to calculate that angle? Arc cosine, absolutely right. So this will be the inverse cosine of 0.975. Because we're told that our target power factor is lagging, we need a positive angle for this guy. So I'm just going to indicate that by putting a little plus sign in front. So the bless you. So that's going to be the arc cosine of 0.975 is 12.838 degrees. And I'm storing that in my calculator as A. And for what it's worth, I stored this in my calculator as T. Okay. Omega. We'll scroll up. So we are told that our system is operating at a linear frequency of 60 hertz. So what is omega going to be? 120 pi. Yep, so just 2 pi times our linear frequency. And lastly, we need to know what the magnitude of the voltage drop across our capacitor is. Okay. So we can see from my schematic diagram here that the capacitor is in parallel with the source voltage. So we don't know what Vs is, but we know what Is is, we know the impedance of our wire, and we know what VL is. So I feel pretty strongly that we can solve for Vs just like we did in that last problem, right? So Vs is just going to be Is times Z wire plus VL. That's from applying Kirchhoff's voltage law. So Is times Z wire plus VL is going to be, let's see, so Is was 295.928 with an angle of negative 28.358 degrees amps RMS. Z wire was 0.1 plus J 0.2 ohms. And VL was 480 with an angle of 0 degrees volts RMS. Let me double check to make sure. Yeah, that's right. So let's see. That's what I have in my calculator as Y times 0.1 plus 0.2 I plus 480. I got 535.505. With an angle of 4.072 degrees. Volts RMS. So what is the magnitude of the voltage drop across our capacitor? 535.505. Great job. And so now I have all of the information needed to plug into that equation for C. I'm going to stop here. I'll let you guys just literally do, actually don't even bother about doing it. You know how to plug stuff in your calculator because I need you to turn in your ICAs. I will provide that numerical calculation when I post the solutions here in about 20 to 30 minutes or so. But we went through all of the process, so now it's just plug stuff in at the end. We just ran out of time. All right, thank you guys for your attention.